Okay, let's look at example 4. Identify a transformation. Each of the given graphs is a transformation of the parent cubic function or parent quartic function. How can you determine the equation of the graph? So we know that the parent cubic function would just be x cubed. And then parent quartic function would just be x to the 4th power. Okay, from here, looking at just the graph, no equation given, can you write an equation by yourself knowing the transformations? So first of all, you do need to know how each parent functions look like. So if you don't know, you should write notes in your notebook so that you can look at it whenever you see something like this. So x cubed by default looks like this, where you have an origin here, 0, 0. And then this is when your coefficient is by default positive 1, right? And so if you plug in 1 into x, your y is 1. So you have the 3 major points, your origin, and then the next point where your x is 1, and your another point when x is negative 1. So why are 1 and negative 1 special? Just because we can plug in easily and just check the positivity or the negativity of your values really quickly. So yeah, you do need at least 3 points to see where where your graph is going, right? So it doesn't have to be a big fancy number. You can just plug in 1 and negative 1. So negative 1 will be a negative 1. Okay, so let's look at the first graph. From this graph, it looks like it's flipped, right? There's a reflection. So it shows that it is a negative function because looking at the end behaviors, it starts positive and then ends with negative. Your original parent function has an end behavior that goes to negative infinity as x approaches negative infinity, and positive infinity as x approaches positive infinity. So if it's flipped, then it means you have a negative coefficient. Okay, so this is going to have a reflection. So one reflection, and reflection means negative. Okay, so negative x cubed is one thing. You also notice that the graph moved, right? It should, so if you just do a reflection from your parent function, it should look something like this, right? Where you have an origin and then you have negative 1, 1 instead of negative 1, negative 1 because they're opposite now. And then you have 1, negative 1, right? But all these points move 1, 2, 3, 4 units to the left. So horizontally, 4 units to the left means h is negative. And then 1 unit down, that means k is negative 1. Okay, so h is negative 4, k is negative 1. Looking at your transformation of function. So there's a transformation of function form. You have plus or minus a times plus or minus 1 over a times x minus h plus k. Okay, remember that. So here you have a x minus h. So when your h is negative, you have to add x plus 4 when you write the function. Yeah, so 1, 2, 3, 4. Yeah. Oh, wait. I'm so sorry. It's not 4, it's 3 because I thought I was moving this point to this point, but no. It's from here to here and then go down because the origin corresponds to this this point in the middle. Yeah. So this is negative 3 and then k is negative 1. So you're going to write a function indicating all these transformations all together. Wait, not f of x. So g of x would just be negative x plus 3 to the cube, don't forget the cube, and minus 1. Okay, so how do we know if the negative is outside or inside? Well, you don't really know just by looking at the graph. So in this case, you can just choose. Okay. All right, part B. So this one, we know it's a quadratic function because the end behaviors both approach negative infinity, right? But you need to know that the parent quadratic function looks like this, right? Where both end behaviors are approaching positive infinity. So this means this also has a reflection over the x-axis. So then you have a negative sign. Okay, reflection means negative. And then if you just have a reflection, you would get something like this, where you have an origin and then you have other points, right? But no. So let's plug in some points to see what were your original points. If x is 1, what's f of x? 1 as well. If x is negative 1, what's f of x? 1. So these are the three major points that we can easily spot from the parent function. Let's see how that moved. So here we're only given 2 points, but actually we can spot the third point here, which is 2, 4. Yeah, it's symmetrical. So maybe, maybe it's not, it is obvious. So maybe that's why they didn't put it, but you can figure it out by yourself. The graph is super obvious. So 1, 5, 0, 4, 2, 4 are the points that we have. You can already see there's a stretch horizontally, or it could be a vertical compression, because your 1, 1 was 1 distance away from 0, 0, right? Both horizontally and vertically. But here, vertically, you're still 1 distance away, but horizontally, you doubled. Yeah, you doubled. Yeah, so, yeah, so there is something happening here. But we want to look at the origin. Origin shifted 1, 2, 3, 1. This is 1, right? 1 unit to the right. So h is negative 1, positive 1. But in the equation, it would be x minus 1, right? And then it shifted up 4 units, and then so that's 0.25, 0.5, 0.75, 4, 0.25. But why is this 1, 5? I'm so confused. Oh yeah. 1, 2, 3, 4. Yeah. What am I thinking? And then so k shifted up 5 units. So k is 5. Right? So we do spot a reflection and horizontal shift. We're not really sure how exactly it might have stretched. Because this point may not be the first point that's here. Maybe you do have oh, this is 1 unit away. I was counting it incorrectly because because it's 2 blocks. This is actually 1 unit away horizontally. Sorry, never mind. So then you don't have a stretch. And just by looking at the graph, it may be misleading, like I just showed you that it may be a stretch, but really, if you look at the points, 1 plus 1 is 2, 4 plus 1 is 5. So really, it didn't really change. All these points are 1 units away vertically and horizontally. So by looking at the graph, it may be misleading depending on the units, right? So make sure you check your units. So the only thing we have here is reflection and horizontal shift and vertical shift. So that's positive 1, positive 5. So at the end, you can write the equation using these transformations, starting from your parent function. Your h goes into your parentheses before you do the power of 4, right? So you have a reflection, negative, represented by the negative sign, and then you have x minus 1 to the 4th power plus 5. Okay, there we go. All right, so if you know the transformation, it's really easy to look at the graph and figure out the equation. If you're not too comfortable with the transformation, I would recommend going back to lesson 1-3 and reviewing the transformations of functions. The cool thing about transformations is that the rules apply for all different types of polynomials. It doesn't matter how many degrees it is you have for the polynomial. The rule works for any type of equation, any type of functions. It doesn't have to be a cubic or quartic. It could be a quadratic function. It could be a log function. It could be exponential function, all that. Yeah, so let's look at try number 4a and b. Determine the equation of each graph as it relates to its parent cubic function or quartic function. So pause the video, see if you can write the equation by yourself, as I showed you an example for. See if you can do it and come back when you're ready for answers. Okay, are you ready? So look at part A. Is this a cubic function or a quartic function? It is a cubic function because the end behaviors approach different ways, right? So is this a negative or a positive function? It is a negative function because your parent function would look like this. It starts from negative and then it goes up. So yeah, this has to have a reflection. And so if you do a reflection, you would have something like this with these 3 major points. And then you see that all of them didn't stretch, but it shifted up 1, 2, 3, 4 times, and then shifted right 2 units. So we have a reflection, we have a translation, 4 units up, and then 2 units to the right. So as a function, how would you write that? So this would be negative parentheses. Make sure you put parentheses before you put the cubic, because if you have an h, it means you need to change the input before you solve for the output. So x minus 2, because your h is positive, and your equation form is in default x minus negative h. And that's a cubic function. So cube plus 4. Okay, good. That's it. And then part B, this is a quartic function. As you can see, it's an even function. So if you know it's either cubic or quartic, you know it's even, so it's quartic. And then this is a positive function because it's facing upwards. So you would have no reflection. But if you look at the major points, all 3 major points moved exactly 3 units down and 1 unit to the left. So that means h is -1, k is -3. So in the equation form, you would have x plus 1 to the 4th power minus 3. Yeah, don't forget the parentheses. Okay, good. Check your answers and see if you got it right. If you did, great job. Let's continue with the final example. Example 5. Apply a transformation of a cubic function. The volume of a box in cubic yards is given by the function v of x is equal to x cubed. The post office lists permissible shipping volumes in cubic feet. Write a function for the volume in cubic feet if x is the edge length in yards. So replace x with 3x because we know that x is the edge length in yards. And yeah. And you can, because this is in cubic yards and you want to get a cubic feet. And you can't just do a conversion like as a one-dimensional, because remember, if it's 1 yard, 3 feet, right? But what about what is 1 yard square? Then you need to figure out 3 feet times 3 feet. Okay, and that is 9 feet square, right? In the same way, 1 yard square would be 3 feet cube. 1 yard cube is going to be 3 feet cube. So we're going to replace x with 3x so that we can convert to feet. And so v of 3x would be 3x to the cube power. And so that's 27x cubed. So the function that represents the volume of the box in cubic feet would be 27x cubed. Okay, let's look at terrarium here. Terrarium is the shape of a rectangular prism. The volume of the tank is given by v of x is equal to x times 2x times x plus 5 equals 2x cubed plus 10x squared, where x is measured in inches. The manufacturer wants to compare the volume of this tank with one that has a width 2 inches shorter but maintains the relationship between the width and the other dimension. So we still want the proportions. Write a new function for the volume of this smaller tank. So this is the original volume. This is the original tank, and we would normally we would just calculate the volume originally by just multiplying all these dimensions, x times 2x times x plus 5, because length times width times height would be just this. But we know that the manufacturer wants to compare the volume of this tank with the one that has 2 inches shorter for your width. So your x is going to be -2, but then it maintains the relationship between the width and the other dimensions. So how do you maintain the relationship like that? Well, in order to maintain the relationship, instead of just subtracting 2 for everything, that doesn't maintain your relationship, right? You have to actually multiply 2 from your x, because original x was doubled for your length, right? And then from your original x, your height is just plus 5. So your original x became 2 inches shorter. So you're just replacing everything by x minus 2. So x minus 2 times 2 times x minus 2 times x minus 2 plus 5. Okay, so you're just replacing x with x minus 2. And then you can simplify. The function would be 2x cubed minus 2x squared minus 16x plus 24. So you do have to think about the relationship when you're just adding everything. Maybe when the problem says when the manufacturer wants to add 2 inches for all the dimensions, then you add all for all the dimensions. But if they just want to add or subtract the dimension from one dimension and then wants to maintain the relationship, that means they're all proportional still. So then you'd have to just replace the original one with the new one in terms of x and the new x equation. Okay, good. So these were 2 examples of application of transformation of cubic functions, where you would change the input or you would maybe shift them, just the input or the entire output. So it depends on the situation where we want to use this transformation. So let's look at trial number 5a and b. The volume of a cube in cubic feet is given by the function v of x is equal to x cubed. Write a function for the volume of the cube in cubic inches if x is the edge length in feet. So we do have the equation already. We want to write a function with using different dimension, which is inches. So you do know that 1 foot is equal to 12 inches, right? So using this information, do the math. and figure out the new equation. Part B, a storage unit is in the shape of a rectangular prism. The volume of the storage unit is given by V of x is equal to x times x minus 1 is equal to x cubed minus x squared, where x is measured in feet. Potential customer wants to compare the volume of this storage unit with that of another storage unit that is 1 foot longer in every dimension. So if it's 1 foot longer in every dimension, then they don't necessarily have to be in the same proportion, in the same relationship. They just have 1 foot longer. Okay, so you just add 1. Write a function for the volume of this larger unit. So this one, you already know the dimensions by looking at the factors, right? Factors here. So you change the factors and figure it out. Pause the video, see if you can solve by yourself. Come back when you're ready for answers. Okay, are you ready? Let's look at number 5a. So using the dimensions that you know, instead of x, if x is already in feet and you want to write it in inches, are you multiplying or dividing by 12 3 times? You are multiplying. Obviously, you need more inches in order to cover 1 foot, right? So instead of x, if x is 1 foot, then so if this is 1x, if this is in feet, right? Then in inches, you need 12 more x's, right? To cover 1 foot. So if you want to rewrite this equation in terms of inches, then you just have to simply replace x by 12x, substitute, and then you cube the whole thing. So don't just multiply 12 from x cubed, then you haven't done it correctly because you only used 1 dimension to the power of 1. But you have a cubic feet and you want to write the equation in cubic inches. So then you would have to replace it and cube your 12x. So then 12 times 12 times 12 would be 1,728 x cubed. So this is your equation. V of x is equal to 1,728 x cubed. Our part B. You know the dimensions. You want to, and this is written in feet. And so the dimension needs to be enlarged by 1 for each unit. So then x plus 1 times x plus 1 times x minus 1 plus 1 is 0. So times x. And then you can multiply this and then multiply by x, right? So x squared plus 2x plus 1 times x would give you the final equation, which is x cubed plus 2x squared plus x. Okay, so check your answer, see if you got it right. And yeah, go look back if you didn't get everything right. All right, let's summarize our lesson. If you look at the concept summary at the end of the lesson, we have compared even and odd functions. So even and odd functions don't always have to, it's not always the same with having even degree and odd degree, but they are strongly related. You can't have an even function when you don't have an even degree, and you can't have an odd function when you don't have an odd degree. So, but even function has a characteristic of a parent function having an even degree and odd function having an odd degree. Okay, but even function means a lot more than just that, just the degree. It is also symmetric across the y-axis. And by algebra, all f of x is equal to f of negative x because they're symmetric. And then odd functions, it is symmetric in the origin. And by algebra, f of negative x is always equal to negative f of x. So you can tell if it's an even or odd by checking through algebra or by checking their symmetry. And then Yeah, and then the end behaviors are going to go the same way for even function. Odd function will go opposite ways. So if you look at the colors, the red will go the same way, green will go the same way. For even, odd, red goes opposite ways, green goes opposite ways. And we looked at transformations of functions, so mainly translation. So if you look at the origin, you can easily see how it moved vertically and horizontally. So looking at that, you can look at the graph and also write an equation for your polynomial function. Okay, good. So we did a lot of understanding of polynomial functions in this lesson. And that should be the end of topic 3. We will review in class after this. Thanks, guys. Bye. See you again in topic 4.